Hello and welcome to DNS design using Amazon Route 53. Today we'll be talking about DNS and how we can use it within AWS to design our applications. I'm James Devine. I'm a specialist solutions architect. To start off with for our agenda, we'll go over just a quick overview of DNS and how it works within AWS and within a VPC and also publicly. We'll then talk about Route 53 Resolver and how we can integrate it with other AWS services, and then get into Route 53 health checks and routing rules, and then finally cover Route 53 Resolver rules and endpoints for hybrid DNS with on-premises environments. So to kick it off here, we'll dig into DNS in AWS and go over an overview of different ways you can integrate and use DNS. Within AWS, we have two different types of what we call hosted zones, and a hosted zone is just a DNS name. So that can be a public hosted zone or private hosted zones. Our public hosted zones are publicly accessible and resolve host names on the internet. We can provide domain name registration, but you don't have to bring your domain name to AWS. You can keep your current registrar and just use AWS to provide your DNS resolution. We have the ability to do some pretty advanced health checks, and we'll get into what those look like. We can also do advanced request routing all over the public DNS infrastructure. For our private hosted zones, these live within a VPC and are accessed through what we call the Route 53 Resolver. They support a subset of the health checks. Obviously, they don't have public IP addresses, and it's all private infrastructure, so it's a little different the way some of our public health checks would work. And we also have hybrid integration using our forwarding rules and endpoints. And we'll cover more deeply on all these topics. Also worth mentioning here that both public and private hosted zones have 100% SLA. So we guarantee that the way we've built our global infrastructure that we can provide this service with 100% SLA, which is a pretty big deal. If we dig into what this looks like in a VPC, this is just a standard VPC, a virtual private cloud. We have an EC2 instance, and in this case, it has a public IP address and an internet gateway to allow traffic in and out. When we configure DNS on this VPC, we have two options here that are relevant. There's DNS resolution and DNS host names. So we can see here we have both enabled. What happens when we enable DNS resolution is it turns on what we call the Route 53 resolver. You may have known this by other things such as the .2 resolver or Amazon provided DNS. We've just standardized on calling that the Route 53 resolver now. So this is an IP address within the VPC. It's the second IP address. So because we have a .0 CIDR here for the VPC, it's just .2, 10.0.0.2. And my instance can query that. And this might seem like kind of a bottleneck or something that's not highly available, but actually it's built in a way where it's highly available and scalable and provides native DNS resolution. So it's a great option for DNS resolution within a VPC, and we provide this at no cost. The second option here is for DNS host names. So we can see we've enabled that as well. And what that will do is anytime we spin up a new EC2 instance, it'll provide a host name. So here we can see we have EC2-XX, that would be the number useec2.compute.amazonaws.com. This provides a way for us to have a public DNS entry for the public IP address. We also provide a private host name as well. And we know when you resolve that host name within the VPC, we'll resolve it to the private name. But outside the VPC, we can resolve it to the public IP address. So a good option there when you need host names quickly and automatically when you provision your infrastructure. Within a VPC, we have DHCP option sets, which control the DHCP parameters, which is the automatic information that gets associated with an instance when it launches, very similar to when you launch an instance in any network. It kind of requests an IP address and additional information as well. So here we're just using the default DHCP option sets, and we've enabled the domain name resolution, and we've also enabled domain names. So both of those will work out of box for any instance that gets provisioned within this VPC. It'll automatically get a host name assigned, and it will have access to the .2 resolver to do all of its DNS resolution. There's some other options here where if we wanted to specify our own custom NTP servers or specify NetBIOS names servers, we do have the ability to do that. You also have the ability to provide your own DNS servers here. So we can see under domain name servers, it says Amazon provided DNS. We would really recommend that you use that for your name resolution. So it's highly available and provides the lowest latency name resolution. We can actually integrate with your larger DNS infrastructure, and we'll talk through some of the ways that we can do that integration. But wherever possible, using the Amazon provided DNS is going to be kind of a best practice to make sure that you can work with other AWS services and features. So let's look at what the DNS looks like when we resolve host names. We can create a private hosted zone that we were talking about earlier. In this example, it's aws.example.internal. So when my instance sends a request and says, what's the name for this, it'll get that response back. And that name resolution will stay local within the AZ and be very low latency. And we just simply provide that host name. We're not going out to any public DNS infrastructure or anything like that. It all just stays within the AZ and resolves locally. Let's take a look at what happens when we do public DNS resolution. Very similar. Let's say we're asking for Amazon.com. The Route 53 resolver will actually go out and look up the root servers and then find .com and then find the authoritative service for Amazon.com and then return the answer back to the instance. And we can see here we actually have both public resolution and private resolution for DNS names. And this is provided out of box. The private hosted zones, we can associate multiple private hosted zones so we can have private DNS names for our VPCs. A common scenario that a lot of customers have is wanting to have what we call split horizon DNS. So have some DNS resolved publicly and some resolved privately. Perhaps like you have internal host names under your main fully qualified domain name that you don't want to expose out to the internet. And conversely, you might want your servers internally to resolve to a private IP address. And that's where split horizon comes in. So in this example, we've added a private hosted zone for Amazon.com to this VPC. So now when my instance creates the Route 53 resolver, it doesn't actually hit the public DNS infrastructure at all. And we can respond back directly with the information hosted in that private hosted zone. So we can control our record set and our name resolution here, and we don't need to reach out to the public infrastructure and can control and almost override what would be resolved publicly is one way to think about it. So we get to do that. We can also take a private hosted zone and associate it to multiple VPCs. So it's not just one VPC. So you can see here, we have our aws.example.internal. We can go into the Route 53 console, and here's a snapshot of what that looks like. And for VPCs that are in the same account, we can just type in the VPC ID there, and then click Associate a new VPC. And that handles that for us. So then we're able to associate that private hosted zone to another VPC. And this works across regions as well. We can have private hosted zones expand anywhere in our commercial regions and have access to those private hosted zones. This also works For VPCs not under the same AWS account, it just needs to be done through the CLI or the CDK to have access to the commands. There's an associate command that you need to run before you do the actual sharing of that private hosted zone. So now my instance in this new VPC can query the www.aws.example.internal and get back the same name as it would if it was in that other VPC. We've just taken that private hosted zone and attached it to an additional VPC. And this can scale out to many hundreds of VPCs. And we have customers that use this to have that common view of DNS between a large number of VPCs. Some considerations here when using the .2 resolver. Obviously, as we've seen in our examples, the private zones take precedence over public. So that's why we're able to do that split horizon and have a different name resolve within the VPC as opposed to out on the public internet. When there's multiple overlapping private hosted zones, we match the most specific zone. So if we had www.aws.example.internal as an additional hosted zone, that would take precedence over aws.example.internal. Each EC2 instance can send up to 1,024 requests per second to Route 53 resolver, and that's typically more than enough. That's quite a large amount of DNS queries. Where we've seen customers come in to hit up against this limit is when they were doing kind of their own DNS proxy, and that can cause some issues if you exceed that 1,024 requests per second. It won't respond to any additional requests over that period, which can result in some DNS name resolution failures. So keep that in mind. If you're using, for every instance, if you're using the .2 resolver, the Route 53 resolver within the VPC, it's not an issue at all. And by and large, we haven't seen any issues with customers hitting up against that when a single instance responds to the Route 53 resolver. Another consideration is private hosted zones don't support delegation. There are other ways that we can copy records between, say, an on-premises DNS server into Route 53, and we have a white paper that talks through some of the ways that you can do that. And also we have blog posts that cover how to accommodate that type of workflow. Now that we've covered kind of some of the basics of how Route 53 and DNS works within a VPC, we'll talk about how this works for some of our AWS services. We'll cover Interface VPC Endpoints, Amazon Elastic File System, EFS, and Elastic MapReduce, EMR. Typically, when we provide AWS services, they have public IP addresses. So you can see here on the right, we have Amazon CloudWatch logs. So for US East 2, we have an endpoint of logs.useast2.amazonaws.com. So when my instance queries that name, it returns back the public IP address of that service. And in this instance, it would return multiple records, but we're just showing one here for simplicity. This means that I need either an elastic IP address on my instance with an internet gateway, or I need a NAT gateway with an internet gateway in there as well. So we need some type of public route to those public IP addresses. What we can actually do with interface VPC endpoints for many AWS services, we can actually create a VPC endpoint, which links directly to that service through an AWS technology called Private Link. So you see here, I can have a private IP address within my VPC. And then when we do that, we can actually associate an AWS managed private hosted zone for logs.useast2.amazonaws.com in this example for CloudWatch. So now when my instance goes to query the public domain name for CloudWatch, it'll get back the IP address of that endpoint. So I've provided access to a public AWS service through private IP addressing and don't need any path out to the internet at all. This greatly simplifies some infrastructure, and also removes the need for internet connectivity to access other AWS services. And here we've shown the endpoint as one IP address, but in actuality, an endpoint is one or more elastic network interfaces. We call them ENIs. So for high availability, we'd recommend 2 or more. You can have 1 per AZ. We can also extend these interface VPC endpoints to on-premises environments and to additional VPCs as well. So if we take our example before and add in an additional VPC here, we can then create a customer-managed private hosted zone. So we'd create a new hosted zone on that VPC, and then we can create what's called an alias record that points to that VPC endpoint. So now when my instance resolves that IP address, or resolves the host name of CloudWatch, it gets the private IP address, and then it can access the service. Here, we just show a connection. This would be like VPC peering. It also works on premises, and we'll get into what some of those architectures look like. And we also have a blog post on how to do this. If we look at Amazon EFS, the Elastic File System, we can have a similar concept here where there's an endpoint, a VPC endpoint, and there's an ENI, an Elastic Network Interface, in multiple availability zones. And we can use both of those ENIs in this example together, but we want to make sure that we keep that traffic local to the availability zone. For example, we wouldn't want the instance on the left to access the ENI on the right, because then it would have to cross availability zones, be a little bit more latency than going directly within the availability zone. So what we can do is if we resolve to the Route 53 resolve error, we actually will get the local IP address of the ENI in that availability zone. And if we do the same thing from the availability zone on the right, we'll actually get the name of we'll return the ENI of the availability zone that's local to it. This is actually using a feature we call availability zone affinity. So there's an affinity for that domain name to resolve the local ENI where possible for the Elastic file system. So this provides high bandwidth, low latency connectivity to an endpoint local to the AZ. The third service we want to talk about was Elastic MapReduce. And generally, as a best practice, the Elastic MapReduce is a managed version of Hadoop. So we spin up that cluster and manage it for you as a service. To make that work, we need a fully qualified domain name for each node. So the best practice here is to, like we showed in the beginning, to enable DNS resolution and host names. And that'll create the appropriate DHCP option set, and then we can have Hadoop work within the VPC without any issues. Now that we've talked about how Route 53 works within the VPC and covered some services, let's get into health checks and routing and what we can do there to kind of route traffic and influence how we do DNS resolution. We have Route 53 health checks. So this checks the health of a specific resource. It can check the status of other health checks themselves, and it can check the status of a CloudWatch alarm. And what that means is CloudWatch is our monitoring service, which pretty much every other AWS service reports metrics to. So we can create alarms on those metrics, say if CPU is high, if network utilization is high, or something just isn't going right, and then we can respond to that. So if we look at health checks with an endpoint, this requires a public IP address and is for public DNS resolution. We actually have a global infrastructure that powers Route 53 that's capable of health checking this public IP address for this resource. So you can see here on the right what that health check status looks like. Everything's moving along and it's healthy. And then we can take action based on that health check. So obviously we wouldn't need to take any action if we have a healthy endpoint. We can also combine health checks. So here we might have health checks from 3 separate resources, and we can do a calculated health check based on those subsequent 3 health checks. And then we can set a threshold. So in this example, my threshold is 2 out of 3. So even though we have an unhealthy health check, we still have 2 other health checks that are healthy. So we still consider this endpoint healthy and don't need to take any action or update any DNS records. This gives us flexibility to build out complicated architectures where we're considering multiple different health checks and failing over only when we need to. We can also use CloudWatch alarms, and this could be pretty much anything within any metric within CloudWatch that you can set an alarm off of. We can take action and update DNS records on. So in this example, let's say we have a private instance and we want to check the status check failed. So something's wrong with the underlying instance, and this value can be 0 or 1. 0 is good, there's no status check failed, whereas 1 is there's a status check failed. And then we can mark that health check status as unhealthy and then take action to fail over a DNS record or update a DNS record. So we have that ability to monitor our infrastructure and proactively make changes so our end users don't notice that there's potentially some underlying issues, or maybe an instance was rebooted for an operating system patch. We're able to kind of fail around our infrastructure and still provide a good end user experience. We have a number of ways to route traffic with private hosted zones, and this also applies to public hosted zones as well for public DNS. Then we'll get into each of these. We have simple routing, which its name implies is fairly simple. You can see here, this is a snapshot of the Route 53 console. We have a record for simple.aws.example.internal, and we have 3 different IP addresses that a name can resolve to. So my instance queries that simple.aws.example.internal. I'll return back what's in that record set, which is those 3 IP addresses. And that works within that VPC because it's a private hosted zone. One of the more simple type of records, which is why we call it simple routing. We also have failover routing. And in this case, we have the ability to, if there's an endpoint that's unhealthy, to update our DNS to resolve the host name to something that is healthy. So this is what our health checks look like for the failover routing. We can see we have an A record for our primary, and then we have another A record for our secondary. So when everything's good, we can query that failover.aws.example.internal, and assuming the first primary node is healthy, we'll get back the record of 1.2.3.4. If it turns out that for whatever reason this instance isn't healthy, perhaps it's been rebooted, or it's just not, it's failing a health check for some reason, then it will be detected and marked as unhealthy. So now when my instance goes to resolve that failover.aws.example.internal, we'll actually get back the healthy secondary endpoint. So this allows us to build highly available and resilient architectures using DNS. So if one node isn't happy, we can fail over to a node that is healthy and ready to serve traffic. One thing to notice here is the TTL values, the time to live. 60 seconds is fairly typical. You might want to set that slightly lower and to be in line with your health check interval. If you were to set those TTL values very large, the DNS infrastructure will obviously update that, but you might run into instances where you cache that within the operating system or your application layer. So you want to make sure to set appropriate time to live values so you can have the failover work the way you need it to. Another type of record set we have is Multivalue Answer. And in this case, we have multiple records and we can return each of them. So if I ask, what is multi.aws.example.internal, I'll get back the full list of IPs that are healthy and available to serve this content. If it turns out we can add health checks here, and if one of these becomes unhealthy, when my instance creates that hostname again for multi.aws.example.internal, I'll only get back the healthy IP addresses. So it gives us a way to kind of have a health check and make sure that we're only returning back IP addresses that are actually up and running and healthy. Another option we have is weighted answer. This is great for things like blue-green deployment, where you want to slowly direct users to a new version of your application or code, or also where you want to introduce incremental changes, or maybe you want to test out a new feature and only extend it to a subset of your users or your infrastructure. In this case, we have 3A records and we have different weighting. So we want half of it to go to our first and then split 30-20 between the next two endpoints. So this weight gives us a way to kind of distribute and fan out that traffic in that manner. So the first time I query that, I'll get back the first answer, the 10.1.1.1. Now, if I have another instance and it does a query, it'll get back the second address as we use that weighting to spread out the traffic. So it'll be 10.1.1.2. So we have a way to spread out that traffic. If then we associate a health check and this record becomes unhealthy, we obviously will stop resolving to that. And then our next request will get back the third address, the 10.1.1.3. So here we've combined a few concepts of health checks and weighted answers to provide DNS resolution that allows us to control the knobs of how we resolve the traffic, but then also we're able to fail around issues that might happen within our infrastructure. And we can kind of wrap together a number of these advanced routing methodologies with a tool we call traffic policy. This is within the AWS console. You can go and build out, it's kind of a flow diagram. So here we've done an A record for IP addresses and then added in a weighted rule. And from that weighted rule, we have a multi-value answer, and that multi-value answer has two endpoints. So, and this can become a whole tree of fairly complicated logic here to control how we route and resolve our DNS queries. So it's a good way to kind of get started and build out some advanced DNS routing through the GUI. Now that we've talked about kind of how we can resolve DNS names and what the infrastructure looks like within a VPC, we want to talk about Route 53 resolver rules and endpoints. And this is really our story around hybrid. How do we take the view of DNS that we have within a VPC and extend it to on-premises, and then also to be able to take our view of DNS on-premises and extend it into the cloud for hybrid DNS. This is primarily accomplished through Route 53 resolver endpoints. They're a fully managed AWS service for DNS resolution. We enable hybrid DNS resolution over Direct Connect and managed VPN. We can also support conditional forwarding rules, so we can route the query traffic where it needs to go. This is a service that we announced at reInvent just about 2 years ago, and it's been very popular with customers. But before we had Route 53 resolver endpoints, a lot of customers were running DNS forwarding instances and managing the infrastructure themselves, having to worry about the high availability and maintenance and management of that infrastructure, which we kind of now just provide as a service with these endpoints. What this looks like in a hybrid environment, here we have a direct connect from our on-premise environment connecting a VPC. You might think, well, I'll just query the .2 Amazon Route 53 resolver. This traffic flow is actually blocked. The Route 53 resolver doesn't respond to DNS queries outside of the VPC. So this isn't an option for doing DNS resolution. And this is where endpoints come in. We have Route 53 resolver inbound endpoints. And an inbound endpoint, similar to the interface endpoint, it's an entity in and of itself, and it contains one or more elastic network interfaces, one or more ENIs. So here, our endpoint, we have two ENIs, so we have high availability, and we span them across two availability zones. So we have that redundancy and resiliency built in to that endpoint. Now when my on-premises DNS server forwards a query for www.aws.example.internal, it'll go through to the Route 53 resolver inbound endpoint, and then from the inbound endpoint, it will reach out and resolve that private hosted zone through the Route 53 service. And then we'll return that answer and send it back to the on-premise DNS server. So in this manner, we have this hybrid environment where we have a completely separate DNS infrastructure in the cloud, and we're still able to resolve it from our on-premises environment, have that true hybrid DNS resolution. And this doesn't just extend to one VPC. We can actually extend this out to many VPCs. So let's assume here that we have an additional two VPCs, and each of them have their own private hosted zone, the aws.example.100.internal and aws.example.200.internal. They each have their own DNS zone that they want to manage. And this is not an uncommon situation. A lot of development teams might want their own DNS that they want to maintain. You might have different environments between dev, QA, and prod where you want to be able to have different domain names that are managed by the individual team within the VPC. But that creates the problem of how do you resolve all of these from on-premises? Well, we can actually take both of these private hosted zones and associate them to this central VPC, kind of like a shared services VPC would be a good way to think about it. And then in a similar way to the previous architecture, our on-premises DNS service can query these records directly through the inbound endpoint. And then from the inbound endpoint, we have access to the view of DNS within that VPC. And since it's associated to aws.example100.internal, we're able to resolve that hostname and return back the record to our on-premises DNS server. So the Route 53 resolver inbound endpoints, they allow this hybrid on-premise DNS server to query Route 53 resolver. The best practice for implementing this would be a conditional forwarder. So you would take the domain name you want to resolve within your VPC and on-premises create a DNS forwarder a conditional forward in your infrastructure, which would allow that name to resolve into the inbound endpoint. It is possible to configure all of your DNS traffic to go to an inbound endpoint, but you probably want to avoid doing that because you want to keep some of your DNS resolution, like public DNS local. But that is an option if you didn't want to have that. These ENIs, the elastic network interfaces, are reachable over Direct Connect and VPN. Nomenclature, just to drive that home, an endpoint is one or more ENIs. We've seen some examples where customers thought they needed an ENI and endpoint for inbound and outbound in every VPC, and it's not the case. We don't need that, and we'll get into an example of what that looks like with outbound endpoints, so we can centralize those and save on some cost there. There is a limit per ENI in that endpoint of 10,000 queries per second, but that can scale up per ENI. So within an endpoint, you'd want two ENIs for high availability, which would give you 20,000 queries per second. But you can scale that up if you needed more queries per second. There's actually a CloudWatch log or CloudWatch metric that you can monitor and alert when you exceed those thresholds in case you wanted to monitor that and were unsure of how much capacity you needed within your infrastructure. Conversely, there's oftentimes the need to resolve on-premise DNS from within a VPC. So a similar example here where we have an on-premise environment with a direct connect into the VPC. Here is where rules come into play. So we can create a rule, and this rule would be of type forward, and the domain name would be dc.example.internal, and that would resolve to, we want that to resolve to our IP address on premises. And here's where we'd use the Route 53 resolver outbound endpoint. So this sits within the VPC and has an IP address attached to each ENI, the Elastic Network Interface. And again, the same concept here where that endpoint is one or more ENIs, so it can have one or more IP addresses, and that's kind of how it scales out and provides high availability and load balancing. So now when my instance wants to go to www.dc.example.internal, that will hit the Route 53 resolver, and then the Route 53 resolver will look at its rule table and see that it has a forward rule, and that traffic will go to the on-premises DNS server, which will respond with the answer, and Route 53 resolver will send that response to the instance so it knows the IP address of that host name. So it's a way for us to kind of extend that view of DNS we have in our on-premise environment into the cloud. This also works for services like Active Directory if we want to provide name resolution to those services, or Microsoft DNS or Bind. It works with those type of services to provide hybrid DNS resolution. And similar as well, very few customers only have one VPC, likely many VPCs in an environment. This works as well. We can share these rules through Resource Access Manager. That's an AWS technology that lets you share resources between accounts. So we can create a Route 53 resolver rule and then share it out through Resource Access Manager. We could share it with our entire AWS organization that's tied to the Resource Access Manager, or we could also share it with individual accounts. We have some options there and how we'd like to share that and have that accessible throughout our enterprise. So in this example, we've gone through with RAM Resource Access Manager, and we've shared that rule and then associated that rule with each of these VPCs. So instances within the VPC can query www.dc.example.internal, and the Route 53 resolver service will kind of in the same manner forward that to the outbound endpoint, and from the outbound endpoint, it'll get forwarded to our on-premises DNS server, which will respond with an answer, and it will get back to our instance through the Route 53 resolver service. What's important to note here is there's actually my two VPCs on the left have no direct connectivity to the VPC that hosts the outbound endpoint, nor to the on-premise environment. So we actually don't need any type of VPC to VPC connectivity required for this DNS resolution. This all happens through the Route 53 resolver service. So in each of the VPCs on the left, the Route 53 resolver is able to forward traffic to the outbound endpoint through this rule that we have shared. Some notes here on the outbound endpoints. At a high level, it's a path for Route 53 resolver to query external DNS servers. We can create source CNIs in a VPC, the Elastic Network Interfaces. It's usable by many VPCs. We can share that out through Resource Access Manager. Similar nomenclature when you go and deploy an outbound endpoint. An endpoint is one or more ENIs. And again, we'd really recommend having two or more for high availability and spread those out across two or more availability zones. And then very similarly to our inbound endpoint, it scales out at 10,000 queries per second per ENI. So having two ENIs will give us 20,000 queries per second. And then we can again watch the CloudWatch metric and alarm on it if we see that those queries per second are getting close to the limit that we have. Within the Route 50 Resolver rules, we have two different types. We have conditional forwarding rules, which we're just showing, being able to forward traffic to on-premise DNS service for specific names on the network. And then we also have system rules. And system rules causes the resolver to selectively override the behavior that's defined in a forwarding rule. So when you create a system rule, resolver DNS queries for specific subdomains that would otherwise get resolved by DNS resolvers on your network would get resolved in some other type of manner. And we'll go over an example of what that looks like. So if we look at resolver rules, when a query comes into the Route 53 resolver, there's some auto-defined rules in a VPC that kind of take preference and happen because they're already defined. So for example, the host names, we have those defined within the VPC, and those would respond based on enabling the DNS host names within the VPC. And then there's also reverse DNS. So some applications will actually send out a query for an IP address and then want to return the host name. And we automatically define those so that the underlying applications can just continue to function without any type of issues because we provide that reverse DNS. So if we look at the flow of traffic through resolver, we can create a dot rule, and this is of type forward. A dot rule for the domain name essentially means that all DNS queries we want to forward to this IP address of our on-premises DNS server. So if we query Amazon.com, even though we have the .2 Amazon provided DNS, the Route 53 resolver local, that can provide this, it's actually going to take this forwarding rule and then forward to our DNS infrastructure. So there's some use cases where some of our customers want to really have a look at all of their DNS traffic and take action on it and whitelist and blacklist. So not uncommon to do this type of thing, and we certainly provide that capability to do so. And then if we had something like a private hosted zone here, since that overrides the forward, and we wanted to create www.aws.example.internal, that would go to our resolver rule. And because that's a system rule that's already defined, we would go and have that private DNS and have that path flow into the private hosted zone. One of the things with that example is that for rules like, or other AWS names like ELB.AmazonAWS.com, RDS, and our relational database service, and a number of other AWS services actually use this AmazonAWS.com name to resolve our service names. So kind of as a best practice, we'd really recommend if you do a dot rule and want to forward everything to a external DNS service, to at the very least have a rule for AmazonAWS.com. And what this will essentially do, because it's a system rule, is it tells the Route 53 resolver to override its forward rule and resolve this traffic locally. So ELB.AmazonAWS.com would hit Route 53 resolver, and then that would be forwarded to the system rule, and the system rule would resolve that out over public DNS, which is essentially local because it's being resolved by AWS. So it's something to consider as you're looking at dot rules and kind of funneling all your traffic to external DNS services. And this type of architecture actually helps out in a number of use cases. I've talked to customers who have external DNS and they want to have all of their traffic go to it, but then services like we discussed earlier, like EFS and our Elastic File System and EMR, Elastic MapReduce, can kind of break if they don't have that proper DNS resolution, and you also add some additional latency. So wherever possible, having AmazonAWS.com as a system rule is a best practice. A quick summary: the most specific rule wins. private DNS, private link endpoints, and VPC DNS get auto-defined rules. You do have the ability to override those. It's a best practice to allow the system rule to resolve AmazonAWS.com. Don't forget recursive records. So there are some applications like Kerberos and others where they need to be able to find a domain name for a given IP address. And we help out there with the VPC site arrangers getting reverse DNS rules automatically. But then again, you can override those if need be. We do have some additional resources if you want to dig a little deeper or this looks interesting for you. The first one is a white paper that we've refreshed just last year that has updated architectures that include inbound and outbound endpoints for hybrid DNS resolution and a number of use cases there. So it's a really good resource if you're considering hybrid DNS and need on-premise DNS resolution. There's also this blog post for integrating Transit Gateway with Private Link and Route 33 Resolver. This talks through some of the concepts that I mentioned with alias records and how you can have that private link, the interface VPC endpoint, resolve into a different VPC than the actual interface endpoint is sitting in. And then we also have 2 YouTube videos here, which are recordings from reInvent last year, one of which is by Gavin, a principal software development engineer on our team that's really good and goes deep into even more detail than I've provided here into how the name resolution works and how DNS works in general. And there's also another video where it's actually a session I did where I talk about routing and resiliency and how to integrate that with Private Link. Hopefully this was a informative and useful session and you got a lot out of it. Thank you for your time. I'm James Vine. I'm a Special Solutions Architect. Thanks.